Okay, so what I'd like to talk about now is something I mentioned before, which is the choice of state variables when we use state space approaches is not unique. We can have all sorts of choices of state variables. We talked last time in the intro what the definition of state variables were. We're looking for system variables, a minimal set of linearly independent system variables, such that when you have the equation of motion, description of the forcing function, initial conditions, you can predict the behavior of the dynamic system for all time. And if you choose a state variable or a set of state variables, and I choose a separate set of state variables, they're going to be related to each other. One set will be a linear combination of another set. And so we can arbitrarily sort of generate many different sets of state variables this way. And the way of thinking about a state variable is just a different way, a different perspective of the dynamics of any one particular dynamic system. So if you choose a set of state variables and I choose a different set of state variables, ultimately they're describing the same dynamic system. So there needs to be sort of some equivalence somewhere in the state space methodology to address the fact that we haven't changed the physical system itself. We've just changed our perspective of the physical system. And so we're going to talk about that a little bit here for the next few minutes. So what we'll do is we'll start off with our state space equations. X the vector dot equals ax the vector plus bu, and y equals cx the vector plus du. For now we'll assume that u and y are scalars. But again, that doesn't have to be the case. And what we're going to do is we're going to say that this is my point of view of the system, and so I am using some state vector which has state variable 1 and state variable 2, so x1 and x2. And for now we'll just assume that this is a second order system, but by no means does it have to be that. This will be a fairly general conversation. You, on the other hand, you've come up with a different description of the system. You've decided to use a completely different state vector, two different state variables, z1 and z2, and you're going to pack that into the state vector z, and your set of state equations is going to be a z, the vector dot, equals a z plus bu equals y equals c z plus du. But we do this because my x vector is different than your z vector. The ABCD that I get is most likely going to be different than the ABCD that you get. And so I'm going to call yours ABCD prime because of that. The input that we both have will be the same, and the output that we both have will be the same, because it's the same system. But you're choosing to describe the state variable in a different way than I'm doing, and as a result, A, B, C, and D are all potentially different quantities. So in my version I've got A, B, C, and D, and in your version I'm going to tag those with a prime. So here's my set of state variables, state equations with this state vector, and here's your set of state equations with your state vector. Now, it's possible for us to figure out what the relationship is between our state variables, and if we can do that, then we can write each of our state variables as a linear combination of the other person's state variables. And so when we do that, let's assume that I can take my state vector x, which is x1 and x2, and I'm going to write each of x1 and x2 as a linear combination of your state variables. So let's assume, just for the heck of it, that x1 was equal to z1 plus z2. And let's assume that z2 was equal to z1 plus 2 times z2. Then what I could do is I could factor out the z1, z2 state vector there, and I would wind up with x the vector, which is x1, x2, equals 1, 1, 1, 2 times z1, z2. So what I've done is I have taken the linear combination that expresses my state variables as a function of your state variables, and I've converted that into a matrix equation. And we'll just let this matrix be P. So I've got some matrix P times Z. So the matrix is playing the role of the set of linear combinations for each of the state vectors. So when I say my state vector is x, and you say your state vector is z, and we've chosen different variables, we now know what the relationship between those variables are. My x is equal to P, the matrix, times your z. Now the interesting thing is to see what that means in terms of how our A, B, C, D matrices and vectors are related to each other. So I acknowledge that x, the vector, is equal to P, Z. And what that also means is that P inverse x equals Z, the vector. So I can think about it in either direction. So what I'll do is I'll come back to my set of the state equations. So I've got x the vector dot equals ax the vector plus bu. And what I'm going to do is I'm going to substitute for the x's. And anywhere there's an x, I'm going to put in a pz. And so I'll note that if I take the derivative of this, the derivative of x dot the vector is equal to pz dot the vector. And that's because the derivative of p itself is 0. So when I look at the x the vector dot, I'm going to substitute a p times z the vector dot equals a times x, but x is pz, plus bu. And now what I want to do is I want to isolate z so that I put the z equation in its standard form, where there's essentially a coefficient of 1, or you might say an identity matrix out front. And so I'm going to want to divide through by p, but p is a matrix, so I can't divide. But what I can do is I can pre-multiply by p inverse. So p inverse times pz, and if I do that, I have to multiply each term over here by p inverse. So I get a p inverse ap times z plus a p inverse bu. This will drop out as identity, and I wind up with z the vector dot equals p inverse ap z plus p inverse b u. And that looks like our standard form. That looks like z the vector dot equals some matrix times z plus some vector times u. So here is z the vector dot equals some equivalent matrix z plus some equivalent vector u. And in this case, the A prime, the A matrix that was in your representation when you use z, is equal to p inverse times my A matrix times p. And your B vector, which is B prime, is equal to p inverse times my B. And now we can do the same thing with the second equation, which is y equals cx plus du. And when I substitute for x, I wind up with y equals c pz plus du. And I'm going to put parentheses around that. And so it's like I'm saying that your c row vector is equal to my c row vector times p, post multiplied by p. And interestingly, our d's happen to be the same in this particular case. And so that's an interesting set of relationships. Okay, if I'm going to write out the new state equations, then what I get here excuse my camera work, is I get z dot the vector equals P inverse AP z vector plus P inverse B times U, and y equals CP z plus du. So here's the new form of the state space equations, and we get that when we substitute one set of state variables in for another. So what this means is, if I have my own state variables, I have x and I have a, b, c, d in my state variable representation, and you have a different set of state variables, we now know the relationship between our a, b, c, d quantities. It also means that if for some reason we choose some new state variables, then we can relate those to the old state variables, then I can use this to derive what the new a, b, c, d matrices and vectors need to be in the new state space representation. And that's a great thing, because we're going to be doing this a lot. We're going to want to be able to choose a new set of state variables compared to the ones we have. And if we already have our state equations, what that means is, as long as we can relate the new state variables to the old state variables, I can use this set of relationships to automatically generate the new state space equations without having to derive them from scratch. And that's going to save me a lot of time. Okay? So that's a nice relationship right there. Interestingly enough, this P inverse AP in linear algebra is known as a similarity transform. When I take a matrix A and I pre-multiply it by an inverse of a matrix and post-multiply it by a matrix, something special happens here. And the special thing that happens is that I'm changing the values in the A matrix when I go from A to A prime. The individual values in the different positions of the matrix will change, but the eigenvalues will remain the same. So I have something known as a similarity transform. A similarity transform looks like a P inverse A P. That is a transform on the matrix A to a new matrix, P inverse AP, and the eigenvalues will be the same. So the eigenvalues are conserved. And the great thing about that, the reason why we think that that's a fantastic thing, is that we haven't changed our physical system. All we've done is changed our perspective on the physical system by going to a different set of state variables. So if I have my set of state variables and you have your set of state variables, but we're describing the same system, the behavior of the system hasn't changed, which means the eigenvalues have to be the same from my perspective and your perspective. And we know that the behavior of the system from the last lecture is provided by the A matrix, because that was in the feedback loop of the expanded block diagram. But we also know when we do this that the values of the A matrix change. So it can't be the individual values that are carrying explicitly the behavioral information. It needs to be something more subtle in the matrix representation. And in fact, it's the eigenvalues. The eigenvalues will stay the same when I convert a set of state equations from one perspective to another, which is the same as saying writing it from the perspective of one set of state variables versus a different set of state variables. I wind up with a similarity transform on the A. Similarity transform is of this form, and the eigenvalues will be